In this video, we're now going to demonstrate the equivalence between Kepler's third law for circular orbits and the Newtonian universal law of gravity. All right, now let's recall what Kepler's third law says. Kepler's third law says that the square of the orbital period is proportional to the cube of the semi-major axis of an orbit. Now, for a circular orbit, the radius and the semi-major axis are the same thing, right? Again, the major axis is the longest point through the circle and or through the orbit. So for a circle, that would be the diameter, and the radius is half of the diameter. The semi-major axis is half of the major axis. So the two are equivalent for a circular orbit. All right. Now, if I have a massive star, and I have a planet orbiting that star at a distance r, then the force of gravity can be written as F equals g times the mass of the star times the mass of the planet divided by the radius of the orbit squared. And the type of force the planet is feeling is a gravitational force, but that force is causing the circular motion. So anytime something has circular motion, it also has centripetal force. So the planet is feeling centripetal force supplied by gravity. Okay? And so we can set these two equations equal to each other. And what we're going to do is solve for the period of the planet and come up with a formula that then also shows that the square of the period is indeed proportional to the distance cubed. All right? So here's how it works. First of all, I can do a little simplification here. My mass of my planets is going to cancel out, and because the radius of my curvature in my centripetal force equation is the same as the radius of the circle here, these can cancel out, right? My radius here can cancel with one of my radii here. So I'm left with this equation. G equals the mass of the star divided by the radius of the circle is equal to the velocity of the planet squared. Now, here's the key. For a circular orbit, the speed stays constant. Right? So for a circular orbit, the speed stays constant. And what is that speed? Well, speed is just distance over time. So if I look at the entire distance the planet travels, then that's just the circumference of the orbit, or the circumference of the circle, and that's 2 pi r. And in what time does it do it? Well, that's the period, right? So the Earth travels 2 pi times the radius of our orbit every year. All right, so the period of our planet is 1 year. That's how we measure the period, in years. In the SI system, it would be measured in seconds. But whatever your unit, the period's going to be in time. Okay, so V is actually equal to the distance the planet travels in the time it takes to do so. All right, so V is just 2 pi r over t. So I can put 2 pi r over t into this equation, and remember that that is also squared. So when I rearrange this, well, the good news is this gives me my t squared, so I have one of my variables. And if I solve this equation for t, then what I end up getting is that t squared is equal to, I multiply this r up to this side, and my 4 pi squared stays up top, so this is 4 pi squared times r cubed divided by g and the mass of the star. Okay, so we've now demonstrated what we had set out to show. We wanted to show that the square of the orbital period is proportional to the cube of the semi-major axis, or in this case, the radius. All right, and so if I have two objects that are proportional to each other, to make them equal, I need a constant of proportionality, so I'll just generically write it down as lowercase k. So my constant of proportionality in this case is 4 pi squared over the gravitational constant times the mass of the star, the more massive object, right? A more detailed analysis shows that this mass of the star should actually be both the sum of the two masses put together. But the reason that Kepler and Newton didn't see that right away, particularly Kepler, the reason he didn't see it right away is because the mass of the sun is so much more massive than any of the planets that his third law held very well without that extra term. Newton did realize that, but not with this simple analysis. It doesn't come out of this. It takes more advanced techniques, all right? But this is your constant of proportionality, 4 pi squared over g times the sum of your masses, times the cube of your semi-major axis. And so even though Kepler was able to arrive at this statement empirically, he just simply plotted the data of the planets that were known to him at the time, and he saw that this relation was true. Using Newtonian gravity, we can then derive that relation theoretically. So that gives a very good bridge between the two ideas and shows that they're actually equivalent. Okay, we'll see you next time.